there, so he got his PhD from the University of Lisbon. He did a couple postdocs in the US and then came back to Europe. So he's got a professorship there. He held positions essentially everywhere. He likes traveling a lot, so he was visiting professor at CERN, at Perimeter Institute in Canada. So I've known Vitor for a long time, so he, as Marta voluntarily put it, he works on the universe. He doesn't work on the real universe, he works on the universe as he would like it to be. So he's got very exotic ideas, but some of them are very interesting. So in particular, he worked on recently on dark matter and its connection with gravitational waves, on superradiance, so the instability of spinning black holes. He worked on quasi-normal modes. So he's got a very broad spectrum of expertise. So I'm not sure what he'll talk about today because the abstract was one line, but I'm sure it will be provocative and interesting. Thanks for being here.
Thank you. It's a great pleasure to be back in Paris. The weather is fantastic. I'm very sorry that I wrote the title and abstract while a student was in the room, and that's what you get when you do that. So I'm here basically to celebrate black hole physics, so I'm going to discuss some aspects of black hole physics. Black holes are a very old and venerable solution of the field equations. The first non-trivial solution was found over 100 years ago, the Schwarzschild solution. Actually, the solution was found basically at the same time by Droste, a student of Lawrence, but unfortunately was traveling while the student was working, and the solution was only published later. It took us a substantial amount of time until we understood exactly the content of that solution, what the solution meant, what it was describing, and what exactly it stood for. We understand nowadays that black holes are very, very special. They are unique in the sense that the most general vacuum solution, which is regular and asymptotically flat, is described by only two parameters. This is the Kerr solution to the field equations, and the two parameters are the spin of the black hole and the mass m of the solution. It's quite amazing that any black hole in the universe, is described by two parameters alone, mass and angular momentum. This is sometimes called the Nohair property of black holes. Basically means that even if you start with a black hole and you just throw stuff in there, all the memory of the infalling matter is lost, and the space-time only remembers the gravitational mass and angular momentum of the infalling matter. So quite amazing. So black holes in this aspect, they are super simple, right? But they are also super compact. In fact, if you try to squeeze too much matter in too small a region, you always end up with a black hole. And this is basically the content of a conjecture. This is called the Hooke conjecture. It's very important to understand black hole formation in a variety of scenarios. And it tells you the following. If you always form a black hole, if you try to squeeze matter, if basically you build a hoop which has a radius equal to the Schwarzschild radius of the object, and that's determined only by the mass of the object, then if that hoop is able to pass through the object in any possible direction, it means the object is a black hole. Okay, this is a conjecture, and to put it in plain terms, you can, even if sometimes you cannot produce a black hole out of ordinary matter, you can always boost matter to make the hoop larger. This is shown here. So I'm putting a person and the corresponding hoop by the person, right? Of course, this is not to scale, right? The hoop is basically proportional to the mass, and this means that if you boost these objects, then the hoop is getting larger. And it must mean, as a consequence, that there's a critical Lorentz boost parameter for which the hoop is able to encircle the persons, and therefore you should be able to get a black hole out of the collision of these two objects, right? And this is the reason why very large-scale accelerators should, in principle, be able to produce black holes. Now, this is a conjecture, but a few years ago, there was a very, very nice study by Matt Choptwick and Franz Pretorius trying to test this. So they took two stars. These are very, very special stars. These are boson stars. They are made of a self-gravitating scalar field. There's some last term because you need to confine the field. And the compactness of the solution is basically 0.1. Okay, so a black hole would correspond to 1. The compactness is 0.1. Now, if you do the hoop calculation, you would expect that at around Lorentz boosts of 5, you'd get a black hole out of the collision, if it's really true, correct? Now, they started with relatively low boosts, so this is a gamma equals to 2 collision. And you see the stars, they collide. The scalar field sees the scalar field of the other star. They just go through. And the asymptotic state are two traveling boson stars, right? Now, at gamma equals 4, and this is still below the critical threshold for black hole formation, you get something nice. You get basically a black hole. It seems like the radius of this black hole is decreasing. This is just a gauge artifact, okay? The area of this horizon is actually increasing. So it's I think it's the most solid evidence that we have for the hoop conjecture being valid, right? So, summarizing, black holes are super compact, they are super dark, just by definition of horizon, and they are super simple. But here, I would like to discuss a couple more, I think, interesting aspects of black holes, and they are the fact that black holes are associated to super luminous events, not the real universe luminosity, as Enrico would put it, but upper bounds, possible theoretical upper bounds on maximum luminosity of any event in the universe, okay? And there are also objects which are super willing to share energy, and I'm going to tell you how we can even use this to do particle physics with black holes, okay, to constrain the mass of ultralight particles if there are any. And if I have time, I'm going to discuss another aspect of this willingness to share energy, which is the fact that they are super absorbers as well, and you could constrain objects without horizons. Very good. So I would like now to discuss with you what exactly do I mean by black holes being associated with super luminous events. So I put in this table some of the highest luminosity events known to mankind. Okay. Of course, the lamp in this room is of order 10 to minus 50 of this Planck luminosity. So the table is listing only really, really luminous events. So actually, I was happy to discover that there's online data for the Chinese Three Gorges Dam. It corresponds to a luminosity of order 10 to minus 43 of the Planck luminosity. This is 10 to the 52 watts. Gamma ray bursts go all the way up to 10 of order 10 to minus 5 of this number, up to, so very luminous events indeed. The events that LIGO saw a couple of years ago, they go to numbers of order 10 to minus 3. If you actually fine-tune it enough and you do a very, very large energy collision, you go up to numbers of 10 to minus 2. By the way, what I mean by luminosity is the maximum number of the rate of energy being radiated at some instant, okay? I'm not talking about total energy emission, I'm talking about energy rate, energy per second, okay? The endpoint of black hole evaporation, if you trust the Hawking calculation, will correspond to a maximum luminosity of around 1 in these units, okay? Of course, you can't trust it because you would need something like quantum gravity to describe the process. But I'm going to argue that you can get very close with something called critical collapse of scalar fields. You go up to 10 to minus 1. And the table is interesting, I think. So we're discussing how luminous any event in the universe with any known interaction can be. Okay, so this is a kind of a fundamental limit on any process. I don't know if it's useful for anything, but it certainly means that if you see something which is of order 10 to 5 of this, it's not regular matter. It's not a regular interaction. Okay? Very good. So there is an old conjecture by Kip Thorne, Freeman Dyson, and I think in a slightly twisted form by Gary Gibbons, that indeed the upper bound on the luminosity has to be the Planck luminosity. The argument is kind of nice. It's very simple. It's the following. So I'm going to assume that there's some shell of radiation somewhere in the universe, and this shell is expanding, so it's carrying energy away from us. Okay? The shell has a width delta, has a total energy m, and it's traveling at the speed of light because I just want to maximize the flux. Okay? Now, if you compute the energy rate that the shell is carrying, you'll find that it's something like, well, mc squared over delta over c. It's a very trivial calculation. Okay? And so the argument now is the following. Okay, I can go back in time and see what happened to the shell when it was looking like a blob, this blob here, right? For the process to be possible at all, I don't want this to have been a black hole. So there's a limit in the compactness m over delta. Okay? And if you impose this bound, then you get precisely that the luminosity by any shell has to be smaller than the Planck luminosity. Okay? It's a very crude argument, but it's been around for decades, by the way. There are some attempts at relating this to some maximum tension principle, but I don't think we've gone very far in that direction. Now, I think the first thing we do when we see some fundamental bound is to try to break it. So there are several ways we could try to do this. First, we can take 2 point masses, each of them carry a charge, and we can try to see, well, this guy is going to radiate gravitational waves, electromagnetic waves. Can we break the bound here? And you can't. Even if you add the luminosity in the electromagnetic and gravitational wave channel, then you'll realize that this, even when they're almost touching each other, is still small, is still smaller than the Planck luminosity. Okay, it's a very 5-minute calculation, very simple calculation. However, I think it's easy, or it seems easy, to violate the bound. If you take, well, if a LIGO binary such as this one radiates 10 to minus 3 of the Planck, of the upper limit, well, I'm just going to take 10 to the 3 binaries, put them all together in an array, and just wait, measure the luminosity, and I'm done, right? So I can do this. I can take an array of LIGO binaries, each separated by some minimum distance d-min, in a way that one is not interfering with the other, so I need to trust my calculation. And I'm going to stack them up in a cubic array of larger size Dmax. Okay? Now there's some things you need to worry about. First, you need to worry about that you need to fix the luminosity of each individual binary to be large. 10 to minus 3 is the upper bound. So you need to make sure that an observer collecting this flux sees that upper bound from all the binaries, right? So you can't have a binary dying off on you while the observer is making the measurement, okay? So I'm showing you here the lifetime of this binary. This is the luminosity, and x is basically the inverse of the compactness of the binary, okay? So r is the orbital radius of this binary. Okay, so this is for a single binary. Now, if you put many binaries together, then the first requirement that the binary doesn't die on you means that Dmax, this maximum size, is at most the lifetime of each binary. Okay? Right? Now, the minimum distance, I'm being very, very conservative here. I'm just going to put the minimum distance a wavelength away. So it scales like this x to the 3/2. Okay? Well, now I can compute the total luminosity. It's just the luminosity of each binary. They are not interfering. There's no interference effect here. You really can sum. And in principle, you can get away with anything. The problem is, if you try to pack too many binaries together, you're going to end up with an array that's inside its own Schwarzschild radius, right? So you need to worry about that. So in fact, the total luminosity of this system is the minimum value between x to the 5/2 and 1/x. When you actually do the calculation and this restriction that this is not a black hole, that this entire array is not a black hole, then you get this number. And this number is smaller than 1. It's kind of amazing. It doesn't mean it's not possible to go beyond the Planck luminosity with this system. It just means I can't trust the outcome if it did. Okay? Very good. So what I'm going to do now is try to see if the upper bound is verified in the original setup that Kip Thorne and Freeman Dyson were thinking about. So I'm going to actually take a shell of matter, and I'm going to see what comes out. Okay? And the first thing we realized was that it's so easy to break this upper bound. So I'm going to start with a very, very simple action. Enrico says I'm an exotic guy, so I'm trying to be as conservative as possible. This is a scalar field, minimally coupled, massless, okay? It's just a scalar field. And I'm going to do the following. I'm going to set up initial conditions that correspond to a Gaussian profile with a certain radius R0. Okay, so this is a shell of matter. It has some Gaussian profile here, and I just let it go. Now, there's two ways of letting this go. The first is that it moves outwards, and the other one, which is the time reversal of this, is that it's moving inwards. Okay? There's three parameters you can control: the amplitude of the wave packet, the location R0, and the width of this profile. Okay? Now, the first set of simulations, I'm showing you something that actually is very easy to understand, and that's the maximum luminosity that this shell is carrying when it's an outgoing pulse. And I'm showing the peak luminosity as a function of the amplitude. The amplitude in some units, okay? This A star is some unit. Actually, it corresponds in the time reversal to black hole formation, but that's not really relevant. And you see that it grows without bound. So you actually can break this so-called upper bound, the Thorne or Dyson bound, very easily. You just take this wave packet, you increase A, and you're done. Okay? Now the problem is that you should guarantee that if you do the time reversal, that in the past there was no singularity, right? You need to guarantee that this is not a white hole. This is not coming out of something that had some singularity in there. So what I'm going to do now is time reverse this. I'm going to study the upper bound on the luminosity if I have an ingoing shell. Okay? And you find the following. Exactly the same setup. I just change a sign here. So this is an ingoing shell. This actually is a classical experiment by Matt Shoptwick in '93, I think, that corresponds to critical collapse. The idea is to tune the amplitude and see when you start forming black holes. Okay? And the result is very, very interesting. So I'm showing you here again the same thing, maximum luminosity as a function of amplitude for different widths, W. Okay? And you find that indeed there is a threshold of order 0.2, the maximum possible value, in the time reverse situation, and therefore these arbitrarily large numbers that you get actually correspond. So from values 0.2 onwards, the time reversal of that situation had a singularity in the space-time, okay? Right? So the conjecture, as we understand it, is the following. There's still an upper bound on the maximum luminosity. The upper bound is the Planck luminosity, but it's restricted to past regular spacetimes. Okay? This is the status as I know it. I think there's ways to challenge this, because the argument is always that you eventually end up forming horizons, but if you somehow are able to stop horizon formation, let's say I put a spherical surface here, this shell is collapsing, and this shell of matter prevents black hole formation, right? So you just increase the amplitude, but now it can't collapse to the center, it can't form horizons because there's some shell. I think you can do that, but then you're going to stumble upon another maximum principle, and that's the maximum tension principle that Gary Gibbons and John Barrow have been exploring for a while. So I'm not going any further in this direction, but I think it's an interesting open problem. Very good. So the rest of my talk, I would like to tell you how black holes are super willing to share energy. This is called superradiance. There are very well-known classical problems about superradiance. The oldest I know of, in the form I'm going to discuss it, is a thought experiment by Ribner. This was a 57 work. And the experiment is the following. I take a two-fluid system separated by an horizontal interface, let's say water here and air here, okay? The air is moving at a speed u relatively to this negative z medium. And what I'm going to do is I'm going to talk. Okay, so I'm in this negative z medium, and I'm going to send a sound wave towards the interface. And I'm going to place a detector, and the detector is going to measure how much fraction of this sound wave is reflected back. Okay? It's a two-line calculation. It's actually done, well, it's a two-line, but it takes a couple of hours. It's done in Landau and Lifshitz, and the result is the following. If the relative velocity u is larger than the speed of sound, then you get back more than you put in. Okay? So the reflected wave is amplified. And of course, the energy is coming from somewhere. It's coming from the kinetic energy of this medium. Okay? So this is translational superradiance. There's also rotational superradiance. I think there's a beautiful analog, and that's the Earth-Moon system. It's not exactly wave superradiance, but let me tell you very quickly because I find this fascinating. You probably know this much better than me, but still, the moon is raising tides on the Earth, okay? And if the Earth was not spinning, the tides would be aligned with the Earth-Moon axis. The Earth is spinning very fast. Well, the moon is sitting there because it's a period of 28 days. There's friction between the Earth crust and the oceans, so actually the tides have some small tidal angle, delayed tidal angle phi. Okay? And because there's friction, you have the planet Earth moving beneath the oceans and dissipating energy. So the day is getting longer, but the Earth is spinning down. And it's a problem because it's an isolated system. The angular momentum has to be conserved, and it's conserved because it's transferred to the moon. So the moon is getting farther away from us. It's been measured, right? Many times. And this means that energy is actually being transferred from the Earth to the moon. It's fantastic. And you also realize that the process is going to stop when the Earth is always showing the same face towards the moon, right? It's the only way that this dissipation can stop. Okay? Very good. Now it's immediate to see that any spinning object is basically going to amplify incoming waves if the phase velocity of the waves is small enough, okay? If the orbital velocity of the wave is small enough. This was something that Zeldovich realized in the 70s, and this is what I'm going to call rotational superradiance. Now, black holes spin, okay? They couple so you need a coupling between the spinning object and the wave, because otherwise you need this intrinsic dissipation in the system, right? You need the coupling. But black holes couple because black holes, spinning black holes, have what's called an ergo region, where everything is forced to co-rotate with the black hole. This is the coupling between black holes and fields. It's not the event horizon. Event horizons are not necessary for this, okay? So black hole spin, you throw a wave of low frequency, the wave is going to be amplified, and these are the amplification factors computed decades ago by President Tchaikovsky. The maximum amplification factor for gravitational waves is of order 140% or so if the black hole is spinning close to maximum and you fine-tune the frequency. Okay? Now this looks like a very exotic phenomena, but you know, it's real physics. It happens every day. And actually superradiance has a number of applications. You can start to do dark matter physics, and I'm going to tell you a little bit about it if I have time. I do. You can actually try to measure superradiance in the laboratory. This was done last year by a group at Nottingham. I think they were the first to actually build a spinning black hole. It's actually a dumb hole. It's an acoustic thing. They threw a wave and they saw it was amplified with amplification factors very close to the ones we predict theoretically. You can actually superradiance does play a role in understanding the linear and nonlinear stability of black hole spacetimes. And it has been playing a very important role in the gauge-gravity duality that high-energy physicists love. Okay? Now, why do we care about this in astrophysics? What connection can we possibly make between superradiance and dark matter? So I'm showing you here a plot that I stole, well, I adapted from a couple of papers, and it's published here, showing you the constraints on dark matter. Dark matter is basically something we don't know, right? We don't control, we know nothing about it. We do have some constraints, and this constraint shows you if dark matter comes under the form of a scalar field, okay, of some mass, I don't know if you can see it, of some mass m in units of, I think, 10 to the minus 10 electron volt, axion-like particle. And the constraint is as a function of, I don't even know what this is. Oh, this is the coupling to standard model particles, okay? And this is exactly the same diagram, but now for a vector field that couples to the Maxwell sector with some strength shown here on the vertical axis. And you can understand that if there's no coupling between the scalar, between your dark matter and the standard model, it's practically impossible to see it, right? If it doesn't couple, you don't see it. But gravity is universal. The equivalence principle tells you that everything falls in the same way. So you see, when most of the experiments are doomed because the coupling is small, gravity always comes to the rescue. And this means that even at small couplings between dark matter and the standard model, you can try to see if you are able to constrain dark matter, you know, in this region. And I'm going to show you that black hole superradiance can tell you something in this region. Okay? From the point of view of somebody who likes fundamental issues, I don't think you need to argue about dark matter to be interested in this, right? You just need to realize that the electron has a mass of order 0.5 MeV. The Hubble scale is of order 10 to minus 33 eV. So you can worry. I mean, have we really tested the 40 orders of magnitude between the electron and the Hubble scale, right? So I think if you can, it's really worth it to explore or see if you can explore these huge orders of magnitude with something that's gravitational in nature, okay? So the very, very kind of simple and raw experiment I'm going to do is the following. I'm going to allow for the existence of massive scalars, vectors, or tensors, okay? And I'm going to see if they're prone to superradiance and if they do something to you. Why do I need a mass term, by the way, for superradiance? I don't. Any massless wave is amplified, okay? But the process dies there. You throw a wave packet, it's amplified, it comes back and it dies off. If your wave packet is of a massive field, then you may get something like this. You throw the wave packet in, it's amplified, but it has to be confined to the vicinities of the black hole because it's massive, right? it has a maximum speed, it has to fall back in the hole, and it's going to be amplified again. This looks like a really, really weak process. But if you do the calculation for scalars, this was done, by the way, by Steve Duttweiler decades ago, the timescales are amazing. For black holes of order 10 to the 6 solar masses, the time scale is 100 seconds if the scalar field has a mass of 10 to the minus 16 electron volt. This is nothing, okay? It means that any spinning black hole, any supermassive spinning massive in the black hole in the universe would be spun down by this scalar field. A month ago or two ago, the similar calculation for vector fields were done. For tensor fields were done. The time scales are smaller for any of these, smaller, okay? 2 orders of magnitude for tensors, roughly, and an order of magnitude for vectors. So they're really even more unstable. If you want to see an evolution, this is what happens when you place a massive scalar field around a spinning black hole, a maximally spinning black hole. You get a lighthouse there. So it is a predominantly dipolar field, spinning, co-rotating with the black hole, extracting energy away from this. This is a real scalar field. It's very challenging to do a full numerical nonlinear calculation because timescales are still large, okay? In units of mass, we're still talking about 10 to the 6 or more dynamical timescale. So this is very complicated. For vectors, if you arrange them, the vector field to be complex, you actually can build a truly stationary end state. And this was something done by Will East and Franz Pretorius last year. This is an evolution. They took a cloud of a vector field around the spinning black hole, and you see as time goes by, this cloud is growing, it's extracting energy away from the black hole is spinning down, and the end state is actually a truly, well, as far as we can see, a truly stationary solution to the field equations with some vector cloud around it. Okay, very nice. So what use is this for? Well, if you're able to extract the energy away from the black hole, and the field is unable to escape, then it's got to be bound somewhere, right? And all the calculations we have show that the field is bound, in fact, to the black hole vicinity. It forms what I am going to call a cloud of particles outside the black hole. The cloud has a typical size that scales like 1 over the square of the mass of the field, okay? I don't think this tells you much, but for a supermassive black hole, we're talking about 300 kilometers, 3,000 kilometers. This can be 10, 100, 1,000 times larger, okay, than that, right? So what happens when we evolve this? How is energy stolen away? How does the cloud grow? And if this is non-axisymmetric, it has to be non-axisymmetric, by the way. If you think about the Earth-Moon system, there's no spherically symmetric moon, there's no, or axially symmetric moon, it's not going to work. It's not going to transfer energy. Moons always have to be non-axisymmetric, and therefore this cloud that grows is also non-axisymmetric. But if it's non-axisymmetric, then it has a non-vanishing, time-dependent quadrupole moment. It should be radiating gravitational waves that we should see, right? And so this is how you can go about and constraining this. But there's another way, because if you're growing a cloud out of the energy of a black hole, the black hole should be spinning down on relatively short timescales. So if you see all the black holes in the universe spinning very fast, well then, maybe this field doesn't exist, right? Very good. So this is an example of an evolution of a spinning black hole in the presence of a field with a mass 10 to minus 18 electron volt. Okay? So this is for an initial black hole mass of 10 to the 4 solar masses, initially spinning at 0.5, the maximum possible value. There's accretion here, okay? So accretion is included, and because for this black hole the coupling is too small, superradiance is basically unimportant initially. It doesn't exist. The only thing that the black hole sees is the accretion disk. The mass grows, the spin grows. But when the mass grows to a value that this coupling is now significant, then superradiance kicks in. The spin goes down. By the way, this is the spin mass diagram, the so-called Reggie diagram. The spin goes down, and now superradiance is getting hold of the evolution. And all the black hole does for the rest of its lifetime is growing in mass, but along a very, very specific line in the angular momentum mass diagram. Okay? You can repeat this for a black hole which is more massive, and of course the only thing that's going to happen is that if the black hole is more massive initially, then the coupling is more significant, superradiance kicks in earlier. Okay? So if you put an ensemble of black holes, say in the beginning of the universe, and you let it go, this is what happens. This is a random distribution of 1,000 black holes with some random distribution of initial masses. Okay? And if you wait for a few million years, actually what you're going to wait is 10 to the 9 years, then what you're going to see at the end is that the distribution has clear gaps in the Reggie plane, in the angular momentum mass plane. Okay? So this is roughly the initial distribution. And this is what, so by the way, again, I'm assuming that there is a massive field, scalar field, of 10 to the minus 18 electron volt. You do not need any initial abundance of this field. This is an exponential process. Any small fluctuation around the black hole would lead to this. Okay? There's no need for any initial scalar field in the universe. So you could start arguing, well, if I overplot known black holes in the universe, known meaning estimates for mass and spin and corresponding errors, and these guys fall outside of this region, so in the gaps that should not be filled, I am constraining the field, the massive field. So these observations would tell you it's impossible. Fields of a mass 10 to minus 18 electron volt have to be excluded. Okay, because we see those black holes. They should not be there, right? In fact, this is exactly how you're able to constrain, for instance, the mass of the graviton. It's a very, very competitive bound just by observing massive black holes. Again, I'm plotting Reggie plane, angular momentum versus mass, and I'm showing you instability windows. Inside these windows, any spinning black hole would be unstable on timescales smaller than 10,000 years. You should not be seeing these guys. Okay? So this observation alone, this is, I think, Farrell 9, if you trust the errors. Okay, some people don't.
I can't read the scale. Does one of these correspond to the astrophysically interesting 10 to the minus 22 electron volts?
No, that's unfortunately, so this goes up to 10 to minus 20.
Okay.
10 to minus 22 requires really, really massive black holes. And I don't think we have nearly enough of those to do that. I think I'm going to try and argue along those lines at the end, but not now. So this goes up to 10 to the 9 solar masses, okay? And Marta doesn't trust it, but let's assume we trust it. It's irrelevant actually for my point, okay? If at some point in the future you have a known catalog of black holes with known mass and spins and corresponding errors, this will give you constraints on fundamental fields. This is the point, okay? For the graviton, this will translate into a bound of order 5 to 10 to minus 23 electron volt. It's impossible to get these bounds with particle accelerators, okay? For scalar fields, the bound is of order 10 to minus 21, 22 electron volt. This is 100 times better, stronger constraint than accelerators can do. And you're using supermassive guys to do this. Okay? So this is my observations typically in the electromagnetic spectrum, but you can do better. If the cloud is there, it's going to radiate gravitational waves. And there was a very, very interesting study by Azimina and the group showing that if the scalar field, so let me stress again, that the only thing you need is a massive field. This is the exotic component, okay? Everything else follows, okay? If the field exists, any field between mass 10 to minus 13 to 10 to minus 11 electron volt should give rise to a number of resolvable events that LIGO should see. And the number is huge. It's over 10 to 5 or so if the mass is really fine-tuned. Right? These are coming directly from this co-rotating cloud around the black hole. A similar number for LISA is not as nice, but if you realize that any spinning object is going to do this, then you can start thinking about stochastic backgrounds, right? And in fact, Enrico, Richard, and other people, including me, did this. And the numbers are fantastic. If the fields do exist, you're going to get stochastic background to a level that you can measure. So this is an example for LISA, for fields of 10 to minus 18 to 10 to minus 16 electron volt, and this would be the LISA threshold. Okay? These guys are really jumping out of your signal. So by collecting the radiation emitted from all the black holes in the past history of the universe, you can get a sufficiently high signal in your detector. So it's fantastic, right? Again, supermassive guys doing this. Now you can ask, black holes are special in the sense that they have an ergo region, a negative energy region, which basically couples the field to the geometry, right? So is the process active for stars? Are spinning neutron stars going to give you something similar to this or not? And it's very, very tricky, I don't think it has been done, to do a full calculation for stars. And the reason is, that most stars, if you trust the equation of state that we love, they are not going to have ergo regions, okay? So that is gone. So the only way you have is to be able to somehow couple the field to the star material. There are ways. If you throw an electromagnetic wave towards me, it does couple to me. I have some conductivity. I couple to the wave. Again, compact stars have a very, very small conductivity, and this is a problem. We did some estimates last year for pulsars, okay? But we think, or it is thought, that the conductivity of pulsars is very small. And this is already an obstacle. If you couple this to the fact that you need a massive field for this, then you need non-trivial physics, okay? Now, if you assume that you have a vector field with some conductivity sigma that I'm measuring in units of standard electromagnetic channel, then these are the exclusion plots that you get for pulsars just from the spin-down observations, okay? As years go by, you measure spin-down rate of pulsars, and this is going to give you constraints because they should be spinning down faster if they are driven by superradiance, okay? So there's some interesting bounds. I don't know how strong or appealing they are. There is something you can do. There's a lot more to be understood here, I think. I have been ignoring also real physics, okay? And typically for axion-like particles, it's not enough that you add, a minimal coupling and it doesn't see the standard model. Most of these fields couple in one way or another, for instance, to the Maxwell sector in this way. The QCD axion has some coupling, it has some non-trivial interaction terms, it has some coupling to the vector. If you add a coupling to the vector, you have two problems. The first is that the mathematics get horrendous, okay? And I don't think anybody was able to tackle this issue. The second issue is you're going to have leakage now, potentially you're going to have leakage from the axion sector, from your scalar sector to the vector sector. So you may not grow clouds as large as they used to be if you shut this off, right? There is a couple of, there are a couple of works conjecturing that you may have laser-like phenomena in the sense that initially, so these couplings are supposed to be small. If your vector field initially is small, the only thing you get is growth of the cloud by superradiance. So it's growing there. This is a coherent state that you grow around the black hole. And at some point, this coupling is going to be important because psi is large enough, right? And the argument then is it may be possible that you get stimulated emission directly into the vector channel. So you may get blasts of light, low frequency light, just because of this coupling. But no, again, I think there's a lot to be understood here. This is really just hand-waving arguments. There is another way in which you can try to see if these clouds grow, okay? And the idea is, again, that the clouds may not be or are not generically axisymmetric, so they look something like this. A non-axisymmetric cloud rotating around a supermassive black hole, okay? This extends all the way up to 10 to 3, 10 to 4, 10 to 5 Schwarzschild radii. So if you're lucky enough, I think you have to be somewhat lucky, but if you're lucky enough that you get enough stars in this region, you see what's happening, right? You have basically a forcing which is periodic. So you have this cloud, it's passing through these stars, it's forcing periodically. You know very well what's the forcing, right? It's the frequency of this cloud, and that's going to either lead stars to resonances, co-rotation resonance, the inner or outer Lindblad resonance, and you should see imprints of this, right? You should see pile-ups of stars close to those resonance points. In fact, there is a curious thing, and I've been told, I'm very exotic, but I've been told that something like this has been observed close to the galaxy center. But another thing that happens if you have this cloud is that the eccentricity of orbits should increase. Okay, this is an example of the evolution of a planet driven by accretion and gravitational drag in the presence of the forcing, and it's sitting initially on a quasi-circular orbit. Okay, and this is mean radius as a function of time, and you see that on large time scales you do find large eccentricities, and they are really just sourced by this non-axisymmetric configuration. So I think I still have 5 minutes, and if I do, let me give you first a list, well, a wish list of things that will take years probably to understand. This was a wish list that I did 2 years ago, or 1.5 years, and I'm very happy to say that the first, which is measure rotational superradiance, is done. Again, the Nottingham group did the observation last year, and I think it's a very solid experiment. But there's a lot to understand. One of the coincidences of somebody that starts studying superradiance is that the maximum amplification factor is always of order 100% or smaller. Okay? It's precisely 100% in large coupling regimes, and I don't think anybody understands why. Is there a fundamental reason for this or not? We don't know. Do black hole binaries superradiate? This would be fantastic, because it gives you an extra scale, and it potentially means you could go down to smaller masses, as was being asked now. Can we go down to constraints on order 10 to minus 22 electron volt just from black hole binary superradiance? If it does exist, we have no idea. What's the end state of superradiant instabilities? The nonlinear, the full nonlinear evolution end state. Apart from this exotic, even for me, complex vector, we have no result on this, and the reason is that timescales are huge. It's very, very challenging to perform this. There was an item on my wish list that was recently tackled, and that's the connection between superradiance and the Penrose process. I think there is a clearer idea of the connection. It's very non-trivial. It's a very non-trivial connection because you see, the Penrose process happens for particles, and these are made of fermions. And fermions have no superradiance. You need a boson to do this, okay? And that's basically because of the exclusion principle. You can't produce anything because it's already there, right? So it's very non-trivial to relate something that's particle-like to something that's wave-like and bosonic. But I think there has been progress. The main open issue, I think, for somebody who cares about observations and constraints, it's precisely this one. How do we know how to couple these fields to the standard model? Do we know how to evolve this? And we don't. We have no idea how to do this. Now, the last 2 minutes, I would like to also tell you that black holes are super absorbers, okay? So let me show you again an example of a superradiant process. I throw a wave packet. You can think of this as the ergo region of black holes, okay? This is just a plot of the effective potential as a function of radial distance. This can be that of a black hole. So you throw a wave, the horizon is somewhere at infinity to your left, okay? And this is roughly the ergo region. The wave packet is amplified, and then each goes their own business, okay? But one thing that you realize is, wait a minute, if this guy cannot go its own business, I have problems. Because I'm sitting in a negative energy region. If this guy bounces back, what happens to it? It has negative energy, right? It can't just leave this negative energy region because it's negative energy, right? And what happens is this. This guy's, I put a mirror here, it's being reflected, negative energy, it has to stay here. When it crosses the boundary, it gives you a positive energy, as it has to be, right? But at the expense of growing, right? It has to grow because it has to be more negative energy, right? And this is kind of fantastic because for those that like exotic business, it means that if you do away with the horizon, you have problems. If the horizon is not here and you have some surface, anything you like, then ergo regions are going to turn nasty. They are going to give you an instability in the space-time. This was something that John Friedman in '78 or something realized very well. We call it the ergo region instability. And now you can start doing constraints, right? If any of the guys out there that I thought were black holes turn out to have some surface, this is going to happen. This is going, again, to turn into an instability that's going to drain the rotational energy away from the object, emitting gravitational waves. I should see this. Right? So we did this study. Actually, this is wrong. It just appeared a couple of days ago, okay? This is the stochastic background that you'd get if your exterior spacetime, this is a huge simplifying assumption, okay? I'm assuming that the exterior spacetime is described by the Kerr geometry, okay? And that at some point I have a surface, okay? And therefore an instability. And what this tells you is that, so this is a plot of the stochastic background level as a function of frequency for objects where the surface lies 10 to the minus 40 away from the horizon. This is a Planck scale, basically, okay? Right, so the surface of this guy is at the horizon times 1 plus 10 to the minus 40. Okay? It looks like science fiction. It means that if you trust everything else, that this is Kerr, and which does need to be, there are small corrections to it, but if you trust this, then the measurement, gravitational wave measurements, are going to constrain things up to what some might call Planck levels. Okay? This is for one of those models here. I'm showing you the stochastic background signal as a function of where I put the surface, okay? And I'm going to put the surface at points such that light takes 10 to the 5, 10 to the 7, 10 to the 7.5 dynamical timescales in this cavity, okay? Okay, so this is still a huge constraint. This allows you to constrain a lot of exotic objects that you have out there. Very good. I think I'm done. I would like to conclude that by saying that these are exciting times for people doing astrophysics, for people doing modeling, and for people doing the future, or how we'd like the field to be in 20, 50 years, okay? Very exciting. Black holes remain the simplest explanation for the observations we have, but I think it's useful to keep an open mind because otherwise you can't see things. You can't see if you are not expecting something. There's a very, I think, elegant sentence by Steve Duttweiler that I like a lot. He used to say that the advent of gravitational wave astronomy would see local observations by measuring the vibration frequencies with the same certainty that we identify the 21 centimeter line via interstellar hydrogen. I think we can go a step further and say, you know, we can see dark matter just from very, very solid, model-free observations of either stochastic or direct resolvable events in LIGO or future detectors. So thank you.
Somehow, right? And the black holes have had some complex history, and there may not be enough dark matter left behind to give you the seeding. Could you say something about that?
Yes. So for the process I'm discussing, the seed is irrelevant. Any small fluctuation does this. We don't need the seed. Any 10 to minus 20 quantum fluctuation in the vicinity of the black hole will lead to this. Right? So actually the background is, I think, irrelevant unless it's very non-accessible. Well, of course it helps if it's there, but it's not necessary. Any quantum level fluctuation will lead to this. This is an exponential cascade. Right? Maybe it takes a couple more e-foldings, but it's there after that. And e-foldings are very short.
Very lovely talk, thank you. So I had a question about the luminosity bound. I was wondering if there isn't a simple way to get around it by having, say, a shell of excited atoms.
Yeah, we thought about it.
And then send a pulse from the center,
right.
and you get a flux density,
yes,
which depends on how thick the shell is.
Yes.
You multiply by 4 pi r squared, you get as large a L as you like.
Yeah, so we thought about it. We actually so when we wrote the paper, we do have even a Penrose diagram for precisely that process, but we can't find, I mean, what we like is a theory, a scalar field with some strange nonlinear potential that could realize this and evolve it, right? But
I'm just talking about ordinary atoms and ordinary light.
Well, but
you don't need any monkey business.
But yes, but you'd like to show it with a simulation that it happens, right? So I'm not sure. So you see, because you need a lot of atoms. Again, you need to show that you're not running into an horizon formation before.
But this is a very large shell, so it's very.
But it's not an empty shell, right?
It's empty, yeah. It just has a little trigger at the center that sends out a pulse.
Oh, but no, but then it's different. So wait, and then how?
So I just have a shell of excited atoms, a spherical shell of some thickness,
yeah,
and some density, and then I send a little signal from the center that makes it laze. Right, so they all de-excite. I now get an outgoing pulse.
I see.
Wave that
I understand.
has as high a luminosity as I like, because it's just.
I understand.
Its flux density is determined by the thickness of the
so
shell.
I think, I think that argument is similar to the argument I had about going beyond the bound, forbidding black hole formation by arranging a spherical wall such that it prevents black hole formation. So I think it can be done, but I think you're going to run into another limit, which is the maximum tension bound. I think your spherical shell has to have a tension that's larger than c to the 4 over g. Whether or not this is a meaningful bound, I'm not sure, but yeah.
I don't see why. Maybe.
Yeah, maybe we can talk. I think, yeah.
Thank you.
And concerning the final state of the evaporation of a black hole, you say that it emits the Planck luminosity, but this has been computed numerically. There should be a numerical coefficient in front of the.
Oh no,
Planck
this is just.
So
No. So this number.
But in principle, it could be done for a Schwarzschild black hole. Just.
So let me see if I understand. So you're referring to this number, right? To this number.
Yes.
No. So this is a very naive extrapolation. You just take the Hawking formula 1 over m cubed, and you extrapolate to the final state.
And 2 slides later, you have also the next one. Yes, you have this power, which is 2 over 5 and
Yes.
of the Planck luminosity, x to the minus 5. This is simply just
isolated binaries.
yeah, but this is an approximation. This is quadrupole formula.
Oh, yeah.
And so this is very crude estimate.
This all of these except for the full numerical calculations are very crude.
Okay.
Except for the collapse are all very crude. But they all tell you the same thing.
Yes.
There might be geometrical factors there, but the numbers are always smaller than 0.2 or so of the Planck luminosity.
But
they are very crude.
do you know any rigorous argument within full GR which points to the Planck luminosity?
No.
Any more questions? Yes.
Stupid astronomer question. I mean, if you plot the maximum luminosity of all objects in the universe, because your table is really fascinating, is there any evidence of a cutoff in the maximum luminosity of all the things there is in the universe?
So I think
the second question was on the Freeman-Dyson. I see that it's cited from a paper on interstellar communication. So what's that about?
Okay. So if you plot the total luminosity of the universe in electromagnetic waves, I think the number is 2 orders of magnitude smaller than this. I don't know it by heart, but it's roughly 2. It's certainly smaller than this. Okay? So all the universe put together. So that's a very interesting thing, the comment. So where is it? So it's here. Yeah. So there's a story. Okay? So we were trying to understand high energy collisions of black holes. It looks like many years ago, but anyway. And at some point, I stumbled across Kip Thorne's monograph where he says, I think there should be an upper bound on the luminosity, and this was discussed by Freeman-Dyson. So I go to the reference, interstellar communication or whatever, and Freeman-Dyson is trying to understand how an alien civilization could extract energy from a gravitationally bound binary. And he shows, well, if the stars are more and more compact, the alien civilization will do better and better, right? And I'm like, what the heck is this thing? I didn't see, but maybe I'm stupid. So in the paper, we reference Freeman-Dyson as cited by Kip Thorne. I went to Cambridge for a talk, and Gary Gibbons comes to me and says, oh, I'm very interested in this stuff. I didn't know this about Kip Thorne and Dyson. Where exactly is this? So I go back to Lisbonne, I send him an email, oh, it's here. Oh, but I don't see this. A day later, a reporter happened to write Gary Gibbons because he was interested in this and the maximum tension bound. And Gary told him, look, I think you should talk to Freeman-Dyson because this is a mess. Nobody knows where exactly this came from. And Freeman-Dyson said, look, maybe, I don't know what happened to Kip Thorne. I certainly didn't do the conjecture. Okay? So this is the status. Maybe Kip thought that, I don't know, that Freeman thought about it and he didn't. But anyway, it's a funny history.
One last question.
Yes, sorry, it's a naive question from an observer. You had a few observed points of black holes with mass and angular momentum. I was wondering, how do you measure the spin of a black hole outside of the gravitational wave? Any possibility, or only through gravitational wave events?
No, so the measurements are of two kinds, right? Either you measure the spectral distortion of K-alpha lines, okay, or through the continuum. I think there's two types basically in the electromagnetic. I don't know if there's some experts here that could tell you more. But this is how you measure, basically because the gravitational redshift and the light bending depends on where in the accretion disk you are and how fast the black hole is spinning. And especially the distortion of the spectral lines, this depends a lot on how close to the horizon the inner orbit goes. So this is roughly how they get their numbers from. I think there's substantial disagreements between two different methods. But still, this is how they do it.
Okay, let's stop here and thanks, Victor.